Welcome students. I welcome you all in this online class. Today's topic is photochemistry of carbonyl compounds. So we'll just begin with the introduction of this topic and then we'll continue the topic with a few examples. And today we'll be discussing photoreduction reaction in that, and then in the later videos we'll be discussing some more reactions like Norris type first reaction, Norris type second reaction, Paterno-Beauty reactions, etc. So first we are starting with the general introduction of photochemistry of carbonyl compounds, and then we'll be discussing the reaction photoreduction. So let us begin with the general introduction of this topic. Carbonyl compounds, especially ketones, they undergo many interesting and versatile reactions on irradiation. Two absorption regions in the UV spectra of ketones are around 285 nm and pi star and 180 nm pi star. Most commonly, the lowest energy transition is N pi star, in which a non-bonding oxygen electron is promoted to a pi antibonding orbital. For many ketones, S1 and T1 are derived from N pi star excitation, and so usually a vessel made of Pyrex may be used for carrying out typical photoreactions. Although the N pi star transition occurs at a longer wavelength, it is always less intense than a pi star transition. We can explain it in the following way, that the electrons in the n orbital are situated perpendicular to the plane of the pi bond and hence to the plane of the pi star orbital, and consequently the probability of the jump of an electron from n to pi star is very low and in fact 0 according to symmetry selection rules. But however, vibrations of the atoms bring about a partial overlap between the perpendicular planes, and so n pi star transition does occur, but only to a limited extent. In contrast, pi and pi star orbitals, they are situated in the same plane, and so pi star transition occurs with a high probability on irradiating the molecule with light of suitable wavelength. Due to the small energy gap between S1 and T1 states, ketones undergo intersystem crossing with a high degree of efficiency, and as a result, most of the photochemistry of ketones arises from their triplet states. So now we'll begin with the first reaction, that is photoreduction. The photoreduction of benzophenone leading to benzphenol is one of the oldest and most thoroughly investigated photochemical reactions. The reaction is carried out by irradiating a solution of benzophenone in isopropyl alcohol with light of wavelength of the 345 nm. Isopropyl alcohol does not absorb light at this wavelength, but benzophenone undergoes an N to pi star transition. So here you can see the equation, that is first equation, which is visible on the screen is that benzophenone, uh, 2C, C6H5, and it reacts with isopropyl alcohol in the presence of light, and benzphenol, that is second, is formed. This reaction can also be performed with a large number of aromatic ketones and aliphatic ketones. Now, one such example is shown here, and that is acetone reacts with isopropyl alcohol in presence of light, and diol is formed. In addition to isopropyl alcohol, a variety of solvents such as toluene, cyclohexane, methanol, etc. have been used for carrying out the reaction. Now let us study the mechanism part. So in case of benzophenone, the initial light absorption is followed by a rapid intersystem crossing from S1 to T1. Now you can see here in the reaction part, the ground state of benzophenone absorbs light and a singlet excited state is formed. Now this singlet excited state of benzophenone undergoes intersystem crossing ISC, and a triplet state of benzophenone is formed. The carbonyl N-pi star triplet is capable of abstracting the alpha hydrogen of isopropyl alcohol, thus giving rise to two radicals, fifth and sixth. So here you can see in the reaction the triplet state of benzophenone. It reacts with isopropyl alcohol to form diphenyl hydroxymethyl radical, that is benzophenone ketyl, fifth, plus 2-hydroxypropyl radical, that is acetone ketyl, sixth. Now we can see here that the combination of two units of fifth, that is diphenyl hydroxymethyl radical, leads to benzphenol, second. Since the quantum yield for benzphenol formation is about 1, the second unit of fifth does not form as a result of the absorption of a fresh quantum of light. Rather, it is generated by the reaction between benzophenone and sixth, that is acetone ketyl. So here you can see the reaction acetone ketyl plus benzophenone gives diphenyl hydroxymethyl radical plus acetone. Benzphenol formation can also be achieved by irradiating benzophenone and benzhydrol in benzene solution. So you can see the reaction. benzophenone and benzhydrol in presence of light leads to benzphenol. And the mechanism of this reaction is similar to that of the above, except that there is simultaneous formation of two radicals which subsequently dimerize. So here you can see the reaction, that is triplet state of benzophenone plus benzhydrol leads to the formation of benzophenone ketyl, and then the final product benzphenol is formed by the dimerization of benzophenone ketyl. Evidence for the participation of excited triplet state in benzphenol formation we'll study and then one by one, since there are two evidences. So the first evidence is the observation that the rate of benzphenol formation is not appreciably decreased when the reaction is carried out with lesser amounts of benzhydrol in benzene solution. This means that the excited state of benzophenone involved in the reaction is a sufficiently long-lived species capable of waiting for benzhydrol molecule. It should therefore be a T1 rather than an S1 species. Now another evidence rests on quenching studies. Addition of small amount of naphthalene to the irradiation mixture reduces the quantum yield to a significant extent, since naphthalene does not absorb light of the wavelength needed for an n-pi star excitation in benzophenone. It is obviously an example of energy transfer in which excited benzophenone molecule returns to the ground state with the simultaneous excitation of naphthalene. Naphthalene thus acts as quencher. Benzophenone must be in a triplet state, not a singlet, which only has a sufficiently long life to undergo collisions for the observed energy transfer with very low concentrations of naphthalene. So that's all for today. So we studied today photochemistry of carbonyl compounds. The general introduction part was covered first, and then a specific example, that is photoreduction, was discussed, and we'll continue this topic in our next video lecture. Thank you so much.